Hydrolysis means to react with water. This word's used in many places in chemistry, but before we start with the hydrolysis reaction, let's just go back and think about how esters are made. We know esters are formed by a carboxylic acid reacting with an alcohol to make the ester and water. Hydrolysis would be the reverse of this reaction, and so we can turn an ester and water in the presence of catalyst and heat back into a carboxylic acid and an alcohol. The problem with this is the best catalyst for doing this is a base. So if I have a base and it's a catalyst, but in my reaction I make a carboxylic acid, what do you think is going to happen to that acid if I have a base present? The answer, of course, is that it's going to react. For example, if you had acetic acid being made and you had sodium hydroxide as your catalyst, we know that an acid plus a base makes a salt plus water, something you've been doing for many years now. In general, that R group could be a methyl group, or it could be ethyl propyl or a very, very long carbon chain. But on the end of it, we still have this carboxylic acid. Of that carboxylic acid, this acid, a hydrogen, is the acidic hydrogen. So during a reaction between the acid and a base, what's going to happen is this acidic hydrogen is going to come off and it's going to join to the hydroxide ion. So there's our acid and our base reacting, and what we would have left would be the sodium salt of the carboxylic acid. So in the case of acetic acid or ethanoic acid, that would be sodium acetate or sodium ethanoate. Okay, so making a fat and oil before we think about making our soap. So just thinking about this in terms of chemistry, when an acid and a fatty acid and glycerol react, effectively this happens in most living organisms in a much more complicated way than this. This is just to simplify it. So we know that we have an acid and we had an alcohol, but this alcohol has 3 alcohol groups. So what can happen is we can add 3 acid groups. So my alcohol will react just as it does in the past, where we have our hydrogen ion or our hydrogen reacting with our alcohol group to make water. What's left is now going to react. So my alcohol is now going to join to 3 different this is called a carbonyl group, 3 different carbonyl groups. So this is my general structure of a fat or an oil. I have a long carbon chain with an ester linkage in the middle and all joined together by this backbone of 3 carbons. So this is commonly referred to as a triglyceride because there are 3 of these R group esters all connected to that one thing. So that's just like we do when we do ester reactions. An alcohol or an OH from one molecule and a H from the other join together to make water, and then we join together what's left. So here is my fat or my oil, and this is what I need to start with when I hydrolyze this oil with sodium hydroxide. Now, normally this would just be a catalyst, but in this case the catalyst will continue to react like we did in the second slide to react. So here is my triglyceride. It has the ester groups, ester linkages in the middle between my 3 carbons that are all joined as a backbone and my R group. Okay, so this is the equation you must memorize, that the fat or the oil plus 3 sodium hydroxides will make the sodium salt of the carboxylic acid, and this molecule, which has 2 names, its common name is glycerol, its correct name is 1,2,3 propanediol. We often signify the structure of a soap as a long carbon chain And then on the end of it, we have this end group, which has a negative charge. So this CH3, CH2, 16, C double bond O, O is a negative ion joined to a sodium ion in this reaction. So how does this reaction work? Again, just simplifying it. Here is my triglyceride, which I'm going to now react with 3 sodium hydroxide particles. And so what's going to happen is the reaction is going to break these bonds here, and it's going to break the, well, there's no real bond between them because they're floating around in water, but it would break apart the sodium and the hydroxide. So now what happens is my 3 carbons are still together, and what they will now join to are 3 OHs, and so we'll make our glycerol back again. I should really spin these OHs around because that oxygen is the thing that is bonded to the carbon. And then I make 3 of these, and these 3 things now are separate from each other, and these are my 3 soap molecules, soap particles that we're going to make. So going back to our original equation, here is my triglyceride. I break these bonds here. I put a sodium onto the oxygen in each case, and I put an OH onto each C in this case, and so I end up with my glycerol and 3 particles of soap. Okay, so here is now the general structure for our soap. Long carbon chain with a charged end. Okay, 3 important words that, or prefixes you need to understand. Hydro means water. Phobic, if you have a phobia, you have a fear, you don't like something. So if you are phobic, you don't like something, you have a fear. And the opposite of that prefix is philic, or suffix, sorry, it'd be used as a suffix. The opposite of that suffix would be philic, which means to like. So here is my soap particle, and now I have a hydrophobic part which doesn't like water, and I have a hydrophilic part which does like water. Hopefully you can see that this charged end is going to be hydrophilic because it will be attracted to the polar water molecules, whereas this long carbon chain is going to not have any polarity associated with it, and so we would consider this to be hydrophobic. It doesn't like water, this end does. Now this unique structure of the soap ion now makes it available to join to grease. Now most grease and dirt and oils are going to be long chains of hydrocarbons. So this hydrophobic tail of the soap is attracted to the grease, and this negative charged end is attracted to the water. And so what starts happening is these tails all start attaching themselves to the grease, and it keeps on happening and happening until you get what we're looking at here, which is called a micelle. A micelle is that brown in the middle is meant to be the lump of grease, and all these little blue are the little blue heads of all of my soap particles, and those little tails are all embedded now in the grease. So if I go back to this picture, so these little tails embed themselves in the grease, the little blue ends are now attracted to the water, and so what we end up with is a micelle, and a micelle is a droplet of grease or dirt or some other non-polar substance that is now completely surrounded by charged soap ions that are attracted to the water molecules. So this is now dissolved and floating around in the water. So the cleaning action of soap now is these steps. So first step is after we've got our grease on our surface, all the little non-polar tails will now start embedding themselves in the grease, with the little heads, the polar heads, all being attracted to the polar water. Now, if there's enough of these little tails embedded in the grease, it will now start to cause a force of attraction and try to lift the oil or the grease or the dirt up towards the water. And as soon as it's lifted up a little bit, then more of these little soap ions start attaching themselves until eventually it's lifted free of the surface, gets completely surrounded by the soap ions and molecules, and now when you pull the plug or wash your hands, away goes the dirt and the grease, and we end up with a clean surface. So, hope you enjoyed the video on making soap. Thanks.